So, good morning. Welcome to Krishna's classroom. I wish every one of you a very happy 2023. Well, we start with a new series of lectures, namely Lebesgue integration theory. But before that, we have to have a look at Riemann integration. And in fact, with this objective, I have done a series of lectures earlier in this channel on Riemann integration theory. It runs through several hours, in fact, and very detailed discussion on Riemann integration. But the objective then was certainly to prepare the ground to introduce Lebesgue integration. Now, what I plan to do is, rather than completely leaving you to look at those lectures, give a very quick review of Riemann integration so that you are this is a sort of self-contained lecture series, and I would take two talks. One, a quick review of Riemann integration. The second one, exclusively on the drawbacks of Riemann integration, or the what one calls the shortcomings of Riemann integration. Because there has to be a certain reason for looking at the concept of integration all over again, and that is probably discussed in the second part of this series, which would be entitled The Shortcomings of Riemann integration. Now, when do the concept of integration occur? Obviously, it did exist in the context of finding the areas and volumes of objects. And it dates back to the before Christ, and to the days of say Euclid and Archimedes. If you were to search for recorded history, and in the Greek, in fact, Greek mathematicians were working on this. Euclid in 300 BC. In his book, The Elements, give a description of computing areas and volumes. In fact, later Archimedes in his treatise entitled The Methods, the method, discusses techniques of computing areas and volumes. And you can see that these techniques were purely geometric in nature. Now, until very late as say the 17th century, when the concept of calculus or the calculus was discovered in various contexts, the integral got redefined as the inverse of derivative, or it was even called antiderivative. This means the following: if f is a given function, on some interval AB, then any function capital F defined on such that f derivative equal to f is called the antiderivative or integral of Now, this is roughly what the concept of antiderivative was. It is embodied in the fundamental theorem of calculus, namely integral a to b where f is as I have described earlier. Now, we shall say more about this later. And of course, whenever such a function existed satisfying this relation, said that f is the derivative of f. Of course, this was not a completely rigorous formulation at that time, but then if you recall your early calculus lessons, you would see that in many cases of the elementary functions, we were finding out the integral, and quite often it depended on even guessing to some extent. And then in some cases there are some methods of getting it out, but in elementary functions we knew from the different theory of differentiation which functions when differentiated will give you a given function, and that knowledge was made use of to define what is called the integral. Now, it was later when they wanted to give a rigorous definition of integration, the concept of Riemann integral came up. Let us briefly recall the definition of the Riemann integral. So, Riemann integration. So, let bounded function defined on a compact AB. Then of course the problem is to compute the area enclosed between the function and the ordinates at A and B and the x-axis. And of course there again what is called positive area and negative area comes to the picture depending on the function is positive or negative. So we shall devise a way of computing this area. Now the figure I draw is for a non-negative function, just to drive home the idea, but doesn't matter, you don't have to assume this. But certainly it has to be a bounded function. Now what one does is this: you partition the domain AB A equal to x naught. So we introduce a partition of AB with x we call this a partition. We call this a partition of the interval AB. Now, on each of this sub-interval xi plus 1 or xi minus 1 psi, we compute the area enclosed by the function and the ordinates at xi and xi minus 1 and the x-axis, that is the shaded region we compute. Now how do we do that? We approximate it. What one does is, let us write down, let minus 1 over the interval xi, 1 xi, and let capital Mi supremum of over the interval xi minus 1. Now this is for I equal to 1 to Thus we have, you see that, you observe that this, since this function is bounded, you see that the supremum and the infimum exist. Okay. Then what we compute is the following. We calculate a lower sum and an upper sum subordinate to this partition. So the lower sum is denoted by L, F, P, which is equal to sigma 1 to n into x1, and upper sum we define as again this well defined, it's a finite sum that comes out, and we are talking about a real valued function, so everything is well defined. Now it is clear that if at all the area enclosed under the curve and the ordinates at x equal to a and x equal to b and the x-axis is given by, lies between the lower sum and the upper sum. I had drawn the figure with a non-negative function, right? Therefore, what we observe is the following. Now, for each partition, such sums are computed. So, we have this formula, namely L, F, P is less than or equal to and you know that this is also true, that is m into b minus a is less than or equal to L, F, P less than or equal to U, F, P less than or equal to m into b minus a, where small m and capital M are small m is the infimum of over AB, small now suppose we refine the partition. What do we mean by refining the partition? Refining the partition means we choose a new partition of the interval AB such that we say P tilde is a refinement of P, if P is the set of points P is contained in, that means there are more points that come into the picture. And then we have this inequality L FP is less than or equal to L is less than or equal to M So you have an inequality of this kind, and says now you look at all the numbers LF for P, and you look at these numbers. Now this collection LFP is bounded above. They are real numbers, and MFP over P partitions where script P is the set of all partitions is bounded below. And from the well-known properties of the real number system, we have the supremum of the lower bounds and the infimum of the upper bounds exist. So we have got the supremum of lower bounds. Lower bounds are and infimum of exists. It's a bounded set of numbers that you have. Once it is bounded above, now you see you get the lower bound, and lower bound above, and then you take all the lower bounds and it has the supremum. So these are what you call the take all the lower bounds, and then you have the supremum exists. Take all the upper bounds, then the infimum exists. Now we call this, so by the lower integral and upper integral, perspective. And denote by designate integral a to b supremum of and LPF. Further, we observe that all upper sums are give a bound for the set of all lower sums, and any lower sum is a lower bound for all the upper sums. Any and any bound for all upper sums. What more you can get? In fact, for any partition P1 and P, we do L P1 no matter what the partition is. Okay. Consequently, the upper integral dx. Now the question is the following: could they be equal? If they are equal, then you say that f is Riemann integrable, and any one of them would give you the so-called Riemann integral. Okay. Equal. If they are equal, then we say that f is Riemann integrable that is integrable in the sense of Riemann. This is the definition. Okay, and we designate the number obtained as the integral of that is integral a to b f dx, integral a to b is equal to, I would write it this way, this so the criteria for Riemann integrability is that the lower integral is equal to the upper integral. So that gives the definition of Riemann integrability. Now, one thing you should observe is that we are talking only about functions which are bounded, first of all. So, boundedness is one of the preconditions that we have imposed, and also we have taken the interval to be a finite. So, let us make a remark here at this stage that compact intervals which can be even, or at least you can say that is bounded, and on bounded functions. This is the a priori this is the precondition we take. So we talk about only bounded functions on bounded intervals. That's the important thing. Now, there is a question. Is it true that every bounded function on a bounded interval is Riemann integrable? Now, it's one thing to define the integral and to know, given a function, whether it is Riemann integrable. First of all, do you have such functions? This is the first question. So, there exist functions which are Riemann integral. For example, one can show that all continuous functions are Riemann integral. So, it's a sufficiently large class of functions. All continuous functions on compact intervals are now this is something to be proved and we skip the proof. Therefore, so let us designate this class by AB, CAB, and the Riemann integrable functions on AB by so we have so every continuous function is Riemann integrable, which assures that we are talking about not something in the vacuum, but talking about a huge class of functions. Okay, right. But not all bounded functions are belong to for example, let us take the function for consider the function is called the Dirichlet function defined by zero and equal to 1 for x belonging to and no one can prove that this is bounded, of course, but not Riemann integrable. That, of course, leaves the question. I mean, it's nice to see how this is proved. It is nice to. It has to do with the what is called the denseness of Q in on the interval or the all rational points on the interval 0, 1 in 0, 1. Okay. So we can So you see that it's large enough. It's a huge class of functions. In fact, continuous functions are a nice, desirable class of functions which we often deal with, and they are all Riemann integrable. But there are some bounded functions which are not Riemann integrable. Now we can make a mention of some of the properties of Riemann. First of all, you see that if f belongs to RAB, if we define maximum of zero x comma 0 for each x f minus x f x 0 then one gets f is equal to minus. Now you see that both, minus of minimum of fx and 0. Then f is equal to, so do you see that this is greater than or equal to 0? This is also greater than. And further, you also have mod f. And one can show that f plus and f minus are AB. And mod f and integral mod f and in fact, of course, needless to say that integral f this is something that you can prove. And further, one of the results that you can immediately prove is this, that if f is Riemann integrable, then further if you define capital F of x dt, then F is uniformly continuous So apart from that, what one can prove is this. So this is uniformly continuous. So we are now listing out properties. So the first one we are writing this, second one we are writing this. You can show that so we are talking about real valued functions only. And further, you can prove that if both fg belonging to then we have integral a to b In fact, what one can write is this modulus of integral a to b for every f a nice property. And of course, the property that I have said earlier that all continuous functions are Riemann integrable. Now, the question is this following. So, if you look at this function, this is called the Dirichlet function. The Dirichlet function is discontinuous everywhere. Okay, every point it has a discontinuity, although it's a bounded function. It's not possible to draw the graph of this function because at all rational points it takes the value 0. At all irrational points it takes the value 1. Okay, and there is no way in which you can draw the graph of this function. But nevertheless, such a function exists. It's a two-valued function. In fact, the maximum value the function takes is 1 and the minimum value it takes is 0. It's a non-negative function and bounded, of course, but still not Riemann integrable. So, Riemann integral, the concept of Riemann integral is not good enough to catch functions of this kind, and this function is particularly sort of a worse kind of scenario where you have the function discontinuous at all points on the interval. Okay. But you might ask the question, suppose you take bounded functions with certain discontinuities. With certain discontinuities, is it still Riemann integrable? That means you don't need, you can go farther from continuity and allow a certain amount of discontinuity for the function. Is it possible? Now to study this, we can use the concept of oscillation, and then you can also talk about what is called the length of the discontinuities and so on. We will just introduce those terminologies so that we are comfortable with whatever we write. Okay, so let me just introduce a handful of terminologies to work on. Oscillation. Suppose function. Let J be a subinterval of AB. Now, what is the maximum oscillation that the function undergoes on this particular interval, subinterval? Now, this we compute as follows. The oscillation of the definition, the oscillation of F on J is defined by and is designated by omega of F J defined as the supremum of f of x for x belonging to J minus infimum of J. What is the maximum change the function undergoes on that? Now, if you want to know the oscillation at a point, as for instance, if you have a continuous function, then at the points of continuity, the function does not oscillate. Okay. Whereas you take a discontinuous function, then you see that the supremum and infimum of, the function undergoes a oscillation. If you approach from the right, if you approach from the left, since we are talking about bounded functions, you approach from the right, and if you approach from the left, they go to different values. That's what we know by saying, that's what we mean by what is called the discontinuity of the function at the point x. If so, we can capture this idea in the following way. We define this as limit the length of, I use lambda for that, length of j tending to 0 for x belonging to j omega. So what you have is that you take the point x, enclose it some interval j, then you have omega fj computed for that, because we have already defined what it is. And then for all j, what happens to this difference? This difference would be bounded, what you call the below by 0, and since we are working on a bounded function, it is going to be bounded above by some number, because we are working on bounded functions. And therefore, you see that the limit of this omega fj as the length of j goes to 0. This is what you call the length of j. Goes to 0. That means x is captured in a, what you call, a nested intervals, and for each nested interval you have this, and then you go to the limit of this. The limit exists, and this limit is what you call the omega fg. Sorry, omega fx, not j. Omega fx. That means the oscillation at the point x of the function f. Now we look at these points. These are some of the notations that we would need to make ourselves pretty intelligible, although we are not going to attempt to prove any of the theorems that we state. X belonging to AB. These are the points where f is discontinuous. So the points of discontinuity of x is designated by d. Then you have dn, somewhere we will come across this, is the set of all x belonging to AB, where omega and d epsilon, there is some discrepancy in the notation there. I think I should go on. You are not using d1 by n, you are using dn, and then you are also writing d epsilon. D epsilon is, there is some inconsistency, but nevertheless it is easier to write d1 by n or d epsilon. So d epsilon we write as x belonging to AB, where omega is greater than or equal to epsilon positive. Of course, I should warn you that there is some discrepancy between these two notations, and if we accept this, then this should have been naturally d1 by n, or this should have been d1 by epsilon. So that you just keep it in your mind, but it's for the sake of writing, properly that without bringing in fractions there, that we use this. We have made two different notations, but it is not consistent. Now let me just make some statement. Now you see that one of the theorems, see, this is some of the questions that you ask. We have defined a concept called Riemann integrability. Okay, so you naturally ask the question, given a function, how do you know that it is Riemann integrable? Okay, we have already said that not all bounded functions are Riemann integrable, but all continuous functions are Riemann integrable. That is something which you have to. In fact, you see that suppose there are some discontinuities. Could this be Riemann integrable? Then there is some estimate that you can get for this. This is the theorem. Let then for every eta positive, there exists a sequence of closed intervals J1 etc. in AB such that D is contained in JK and so suppose you have a Riemann integrable function. Then one of the properties that you can see is that you cannot have wild discontinuities. Now this is what it says, like the Dirichlet function that we have looked at. Here what it says is this: suppose you look at the set of all discontinuities of f denoted by D, we have defined it, and then D can be packed inside a countable collection of intervals, closed intervals Jk. Okay, that means D is contained in a and this you can do. See, given any eta positive, no matter how small eta is, there exists a collection of intervals J1, J2, etc. such that D can be packed into this, what do you call the, sorry, should not use sum here, it's union of k from 1 to infinity jk, and such that the sum of these intervals, the length of these intervals is less than eta. So all Riemann integrable functions have this property, and you can immediately check that, verify that. satisfy this. In fact, you see that the entire interval 0 to 1 is points of the sets of discontinuity. And you see that the smallest interval in which it can be put in is an interval of length 1. So this result is not valid for any eta positive. In fact, any eta less than 1 does not fit into this case. Okay. So that is an important observation. In fact, one can prove this theorem. Okay. Right. Now we define what is called a null set. Now these are some of the terminologies that are required to make our results intelligible. A subset said to be a null set if given epsilon positive, there exists a countable family of intervals countable family IM such that E can be packed inside IN and then that means for every epsilon positive there exists a countable collection of intervals such that E can be packed into the union of that and such that the sum of the lengths of these intervals is less than 0. Then you say such a set is a null set. In short, what you are going to say is that the limiting length of the D is going to be what you call equal to 0. Okay. So we see that obviously the Dirichlet function or the set of all, if you have a finite set of points on the interval AB, then it satisfies this property. Even a countable collection of points do satisfy this property, but certainly not the whole interval, nor if you take all the set of all irrationals, they also do not satisfy this property. Therefore, let us look at some examples here. Every finite set of to, I'll come back to this null set later in the context of what are called sets of measure 0, etc., etc. later. Any countably infinite set contained in the third example is fascinating. Now I'm going to talk about a new set called the Cantor set. There is a very detailed discussion of this Cantor set in my first series of lectures. You can go into that or have a look at Rana. There is an integration theory by Rana, beautiful book, and there you can see this discussed in detail. But I would refer you to my lectures where I have analyzed these sets and their properties properly. This is called the Cantor set, famous one. The Cantor set C alpha, where 0 less than alpha less than 1 is not a null set. Not a null set. Whereas C1, that means the Cantor set C1 that is corresponding to alpha equal to 1 is a null set. Now we can prove some theorems which tells you or connect the Riemann integrability with the sets of, with the structure of the set of discontinuities of the function. Okay. Yeah. So remark to analyze the Riemann integrability, we look at the sets d epsilon associated with namely d epsilon defined as the oscillation at x is greater than or equal to epsilon. If or we expect d epsilon to be a null set for each epsilon positive, for f to be integral. And we already seen that d epsilon is not a null set for every epsilon in the case of unless of course you take epsilon to be greater than 1. So there are some values of epsilon for which d epsilon is not a null set in the case of the Dirichlet function. So that is what you expect. So we have in fact theorems of this kind looking at the properties of the d epsilon. If f belongs to then d epsilon is compact. That is one of the results. Now another result that is a pointer to this is that if f belongs to RAB such that suppose f is a bounded function. If f is a bounded function, on AB such that D is a null set. Then f is Riemann. So one of the sufficient conditions for bounded functions to be Riemann integrable is that D is a null set, the set of discontinuities. That means you cannot allow too far or far too large or even a significant, I would put it this way, even a significant I would put it this way, you cannot have that set of discontinuities to be of significant size. Okay, that's the meaning. It should be a zero size. Okay. For example, so this, you see, this allows a lot of things. You can easily analyze now. If you are given a function, you look at the discontinuities, and then by looking at the points of discontinuity and whether it's a null set or not, you can easily decide whether it is Riemann integrable. If it is of null set, it's a null set, then certainly it is Riemann integrable. Okay. Example, let that is the characteristic function of the Cantor set C alpha, then, or I will put it in the bracket, characteristic C alpha. Then f belongs to if and only if alpha equal to 1. And in such a case, integral 0 to 1. What this result says is this. If you look at the interval 0, 1, consider the function or you look at the what you call the Cantor set on the interval 0, 1 and define the function to be the characteristic function of C alpha. That means for points in C alpha it is equal to 1 and the complement of that it's equal to 0. Now then what you have is that f is Riemann integrable if and only if alpha equal to 1. And in such a case, integral 0 to 1 fx dx equal to 0. That means on everywhere except on a set of lengths, I put that in inverted commas, in a set of length the function of 0, the function is 0. Therefore, the integral is 0. Whereas when alpha is strictly less than 1, then you see that C alpha is significant. It's not a null set. And in that case, the corresponding characteristic function of C alpha is not going to be integral. That's it. Okay. So this gives some insight into the role of discontinuities in deciding whether a function is Riemann integrable or not. Okay. So you cannot entertain far too many discontinuities. At a modest level, it is accepted. That means you can go beyond what are called continuous functions, but cannot allow arbitrarily discontinuous function like the characteristic function of Q intersection R or 0, 1. Okay. That is the Dirichlet function. Now we will come back to the connection between the derivative or the differentiation and integration. Recall that after the advent of calculus, the integral was identified, for nice functions, was identified as the antiderivative of a given function. This is valid for nice functions. And in fact, the fundamental theorem of calculus throws some light into this. So let me just write down the fundamental theorem. We state the theorem. This is one of the deep results of analysis. Let RAB zero and f of x is defined as integral 0 to a to x ft dt. for now this is well different. Okay. So F is capital F is well. Some statement we have already made about this, and we repeat that as part of the theorem. First observation is that capital F is uniform continuous on two if F is continuous X, then capital F is differentiable at X, and what we get is the following: F derivative for such X. So the condition that you need here is that F is continuous. The third property is this. If there exists G is any differentiable function on AB such that G derivative AB then for every X comma Y belonging to AB, GY minus integral X to Y. So this is, so look at these results. First of all, this is well defined, capital F is well defined, and such a function is a uniformly continuous function. It does not mean that the function is differentiable automatically everywhere. Okay. Now, wherever the function small f is continuous, capital F is differentiable, and at those points f derivative is equal to g small f. That means there are points where the differentiability of capital F is questionable, although this kind of result can be easily a function of this type which is uniformly continuous can be created. Further, if g is any differentiable function on AB such that g derivative is equal to f, then you have the classical fundamental theorem of calculus, namely gy minus gx is integral y to x to y f dt. Okay. Now you see, before this the Riemann integration came into being, it was assumed that this result holds, this relationship holds. Okay? And it was a startling, revelation that this is not necessarily true always. Okay, so the differentiability of f is suspect. It could happen that the g is not differentiable at possibly several points. Because for Riemann integrability, you don't need the continuity of the function. Okay, right. Okay, so that in a way gives some insight into Riemann integrable functions, and possibly we have to look at some of the outcome of this in our next lecture, where we would analyze some of the drawbacks, or what you call not drawbacks, some of the shortcomings, some desirable results that we would have liked to have is not there, and these aspects we would have highlighted and making a case for having a relook at the concept of integration. And that obviously led to one of the remarkable mathematical theories that came out in the 20th century, namely the Lebesgue integration theory, which had a lot of deeper ramifications. And I think this is a nice place to stop. And later, after doing this, going across to Lebesgue integration theory, obviously Lebesgue integration theory gives many more functions integrable in the sense of Lebesgue. And you can show that this is a genuine extension of the Riemann integration theory. And you might ask, what exactly is can you characterize Riemann integrable functions in terms of Lebesgue integral? So we have the Lebesgue-Vitali theorem in this regard, which we will prove that f is Riemann integrable if and only if it is continuous almost everywhere. That means, in the sense of Lebesgue measure, the size of the set of discontinuities of the function is 0. Okay, but we will say more about this, because this almost everywhere concept, etc., we will introduce at that time. We will come back to this theorem. But I just want to say that it's a sort of a necessary and sufficient condition for f to be Riemann integrable is that it is continuous almost everywhere. So let me just put that theorem here. Eventually, after going through the Lebesgue integration theory, this is what we have. What are the Riemann integrable functions? Can you characterize them in terms of Lebesgue integrable theorem? This is due to, this is Lebesgue. F is Riemann integral. If and only if is continuous almost everywhere. In fact, you see that the Dirichlet function that we have defined is integrable in the Lebesgue sense, but it is not integrable in the Riemann, in the sense of Riemann, because the set of discontinuities of this function is everywhere. Okay, so it's not a set of measure 0. That's what you mean by almost everywhere. Anyway, unless you introduce the concept of measure, it does not make any sense to talk much about it. Okay, thank you very much. So that gives a very brief introduction to Riemann integration for you to for a quick reference of whatever is happening. But this has been very elaborately discussed in several lectures, giving details of quite a lot of things. Like one thing I would like you to look into is all these aspects of oscillation, etc. D, epsilon, then the what you call omega f x, the definitions of all those things, and further what you have is this, especially the Cantor set, because the Cantor set provides you with beautiful examples, or many pathological situations can be constructed out of the Cantor sets. They are such beautiful things. Okay, so thank you very much.